In this lecture, we will overview the device fabrication techniques. So we learned in one of the previous class that quantum transport, and especially quantum ballistic transport, happens in this length scales or in this dimensional scales, where the length or dimension of the device is less than the scattering length or the phase relaxation length. And for one of the most popular two-dimensional systems, which is based on gallium arsenide, this elastic mean free path length, LE, is few micrometer, maybe couple of tens of micrometers. And the phase coherence length is something like close to a micrometer. And for silicon, this elastic mean free path is only a fraction of what you can get in gallium arsenide as per the current state of art, whereas the phase coherence length is close to what you have in gallium arsenide. So what that means is the length scales need to reach this dimension or even lower to observe the quantum ballistic transport in devices based on these materials. Okay. And here is a picture of the first transistor, which is like close to like a centimeter. And what we have here is the latest FinFET, which is something like 7 nanometer of the pitch or the least dimension, which is well defined, which is defined in that device. It's kind of the gate dimension. Okay. So now this revolution of taking the device dimension from like a centimeter to 7 nanometer scale has happened over many years with a lot of complicated and sophisticated technology. And these are highly expensive and very complicated technology which runs in the industrial scale, multi-billion industry. But as far as laboratory research is concerned, we don't have access to many of this technology. And in this lecture, what we will do is we will overview what is generally available in research laboratory based on universities and institutes for fabrication of devices where you can observe quantum transport features, quantum transport phenomena. Okay. So we will not dwell into the details of the industrial scale manufacturing. That is not our aim here, but we will discuss what is generally available in universities and research labs for fabricating nanoscale or microscale devices. Now, let us take a quick look at the length scales that we are aiming. Okay, so as we have discussed, the length scales are where we need to see single particle spacing or single particle phenomena are like few hundreds of nanometer. You can also observe this in lower dimensions, but that require a lot more sophisticated fabrication technologies. So what is generally available is like few tens of nanometers to a few hundreds of nanometer to like a micrometer, which will operate in the cryogenic temperature regime, like below 4 Kelvin or below 1 Kelvin. And that is the physics and that is the technology that we are going to discuss throughout this lecture. Okay. So what we are aiming here is something like a micrometer or below in dimension. Okay, that is our aim. Something like a micrometer or below in dimension. That's what we are interested in. Okay. That is what is required to observe single particle spacing or single particle phenomena, the quantum or quantization due to confinement at temperature ranges below 1 Kelvin. Okay. And there is also another aspect, that is the single electron charging phenomena. And these are the length scales and these are the temperature scale which is required to observe this. So here also around liquid helium temperature, you need to go below few micrometer of the order of micrometer to observe the single electron charging phenomena. But remember, this single electron charging phenomena is not strictly a quantum mechanical effect. It's a classical electrostatic charging effect, which we will discuss when we discuss quantum dots and tunnel junction in one of the upcoming modules. So in a nutshell, what we are seeing is we need devices with submicrometer dimensions to observe most of this phenomena. And that is the main topic that we are going to discuss in this lecture. Okay. Now, the length scales or the dimensional scale are in like a few micrometer to like a few nanometer range. And this regime is actually called mesoscopic regime. Microscopic regime consists of atoms, molecules, and clusters like a nanometer or below. And the macroscopic regime, in this case, is like your macroscopic objects that you see. Okay, for example, tennis ball or a period, a full stop. Okay, and if you go further down, you have the blood cells, then bacteria, then virus. So we are actually in this length scale where the device are few tens of nanometers in size. Okay. Now, this dimension is called mesoscopic regime or mesoscopic. The devices are called mesoscopic devices. Okay. And just for comparison, the human hair is approximately 50 to 60 micrometer in diameter. Okay. And to reach this dimension, either you can start from the microscopic and to reach the mesoscopic regime, where you can basically assemble atoms, molecules, clusters, okay, and reach this regime. Or you can start from the macroscopic regime, where you start with the bigger material and chop it down with various technology and reach this regime. Okay, those are the two methods. This is called top-down method because you are starting from the top, from macroscopic or bulk material and marching down. And here this is called bottom-up because you are starting from the lowest atomic scale and reaching the mesoscopic regime. And both of these regimes got its own advantages. Here it is a low-cost method. You can even get much lower dimension that you will realize once we discuss the top-down fabrication methods. But the issue here is it's not really scalable. If you want to make an array of devices or a wafer full of devices with similar dimension or identical design, this method is not really suitable for that because these are kind of self-assembled structures. And whereas top-down is highly controllable and precise and it's scalable, and that is what generally the semiconductor industry relies on. But the issue here is you cannot go beyond certain dimension. That is basically decided by the resolution of the process that you are using to make this device. So here you have a table which size scale, okay, where and how this process has been evolved over the years. Okay, so now you can start from the top down. So you start from like few, hundreds of micrometer and go down. That is how the device started. Okay, or device technology started. And here it's a bottom up where you can use chemistry and various self-assembly, self-assembly methods and reach this regime. Whereas here you can use precise and microfabrication machining tools, lithography, and all the other technological gadgets to reach this regime. And finally, you are going to hit this regime, which is your mesoscopy regime. It's like a few tens of nanometers in size, this regime. Okay, that's what you are going to reach eventually. Okay, here. Now, the essential tool, okay, to reach this length scale is lithography. Okay, so that is the heart of microfabrication, and all other process actually accompanies the lithography process. So lithography is probably the most important aspect of microfabrication tool, without which you cannot have any microfabrication tool. Microfabrication, okay? So lithography is the heart of top-down approach, and that is going to be the main topic of discussion in this lecture. Here, the term lithography originates from an ancient printing process. Okay, so what you have here is you have some kind of a stone, okay, litho means stone, okay, and you can draw whatever the pattern or whatever you want to print using a greasy substance. Okay, whatever you can draw here, that you draw with a greasy substance. And later on, what you do is you moisten the stone with water, and the parts of the stone not protected by the greasy paint will absorb water, will get soaked with water. Okay, but the ink that you are going to use is an oil-based ink. Once you roll that ink onto the stone, the ink will stick only to the greasy part, while the wet parts will not absorb the ink at all. And then what you can do is you can just press a paper onto it, and wherever the ink is, that will get transferred onto the paper. And you repeat this process. This is historically, this is how in ancient times printing had happened. And this process is called lithography, and this word lithography originated from this process. But what we are going to discuss here is something slightly different. It's kind of a stencil painting, where you have some kind of stencil and you apply paint over the stencil, and that gets transferred onto the substrate or onto your hand here, as shown. Okay, so this is the technique. This is the technique that we are going to discuss, but in a slightly different context, where you use the stencil and everything are basically highly sophisticated gadgets which you use to create the pattern. Okay, now here the lithography involves, in microfabrication, the lithography involves use of energetic radiations or energetic ions or electrons. Okay, so the process is like taking a picture where you have some kind of a chemical which will undergo a chemical change when exposed to this radiation or ions or electron, and that part, wherever it was exposed, can specifically remove or selectively remove, and you can get a stencil of the pattern which depends upon wherever you have expose the radiation. Okay, so for example, there is a substrate here, and you have a polymer which we call a resist, okay, which is coated on the substrate. Okay. And you have a stencil, it's a thick black line here, which is placed on top of this substrate, which is coated with this polymer. And when you expose energetic radiation, wherever the radiation goes through, that is, wherever you have openings or transparency on this mask, the places under those region will get exposed to radiation and will undergo a chemical change. Okay. Now, depending upon the type of the resist, you can broadly classify this as a positive resist or a negative resist. A positive resist is something which undergoes a chemical change when exposed to radiation. And the chemical change is such that you can dissolve that region in some other solvent. Basically, you have a long chain of polymer, and whenever the radiation hits on the polymer, the chain will break into smaller chains, smaller pieces, and you can easily dissolve that region in certain solvents. Okay. So, for example, for a positive resist, we call a positive tone resist. This region, wherever it gets exposed to radiation, will undergo chemical, will get broken, and you can dissolve and remove. So you've got a stencil on top of the wafer, on top of the substrate. Wherever the radiation has hit, those places, the resist has been removed. Okay. Now, this process is called developing. So you coat the photoresist, okay, and you expose with the radiation, then you develop. Then what you can do is you can basically create patterns either by etching. So wherever the resist is not there, that place is exposed for you to do further processing. So either you can actually etch it down, that means you can remove material and create a profile, or alternatively you can also deposit metal or dielectric materials or other substrate, other materials, and you can get layers of the material that you are going to deposit on this substrate. Okay, and eventually you can remove or strip the polymer, and you got a etch pattern here, or if you have deposited, you get a pattern metal on top of it, or whatever material you have deposited on top of it. There are two processes. Either you can remove or you can add material onto substrate. Okay. Similarly, the negative tone is just negative of this process. So wherever the radiation has hit, that will undergo a hardening process, or that will undergo a polymerization process, and you can remove the rest of the region using a solvent, which is the process of developing the resist. Then you will just get the negative of whatever your original mask was. So this is your original mask, and in this case, you got a positive of this mask. This is a positive, or the same pattern that has been transferred onto the substrate. In this case, basically, you get a negative, or just inverse, so it's opposite of whatever you had on the mask. That is the pattern you got. Again, similar process you can do, whether you can add material or you can remove material further, and eventually you can strip the resist, and you will get the new pattern which is transferred onto the substrate. That is the process. So generally, there are two things that you do. Generally do. That is, either you after photolithography or after lithography, you metallize it. That means you deposit metal, or you basically etch it or remove material. So you have the wafer with the photoresist. Then after lithography, you get a stencil. You remove wherever the regions are exposed. Then you can add material that is represented by this red colored region here. Then you strip the places where you had resist on top of it, and you will get this pattern. Or conversely, oppositely, you can also do the same process, but instead of depositing, you can remove the material, and you will get that profile onto the paper. So lithography essentially involves you create a stencil, you create a pattern, and then you can add material into the pattern, or you can remove material using the pattern. Okay, so that is essentially the process of lithography. And this lithography you can do either by energetic radiations such as ultraviolet radiation or X-ray radiation, or you can also do with charged particles such as electrons and ions. So both of these processes we will discuss in this module. So let us look at first the optical lithography in somewhat detail. So what you have is you have some kind of a light source. Then there is something called a mask which defines the pattern, master pattern, and there is some optical systems, okay, which defines or which will give you a parallel beam, and you have photoresist coated substrate and rest of the process. But after lithography is what we just explained the previous slide. So essentially this mask which contains the pattern is a glass or a quartz plate which is coated with some chromium, and then that chromium has been patterned to whatever the desired shape which you are going to get transferred onto the substrate. Okay, now there are three modes that you can do the lithography. One is called contact mode, and second is a proximity mode. It's almost in contact. You can say soft contact. This is a hard contact, and there is a projection mode. Okay, so in the contact mode, whatever the substrate that you have, that you hard press onto the mask and then expose to the radiation. So in this case, you will get a one-to-one magnification, and you can also get a resolution which is like a fraction of a micrometer. The issue in this case is the contact can actually degrade the mask when you reuse it, and you can also introduce particulates from the mask onto the substrate. So this is kind of less cleaner process. Okay, but you can get a much better resolution compared to the soft contact mode. So it's a proximity mode where this almost pressed onto the mask, but you are inevitably going to have some gap between the mask and the substrate, like a couple of micrometers. Okay, in this case also you will get a one-to-one magnification, but the resolution is limited to like a couple of micrometer. That is because of the diffraction effects, which we will discuss very soon in the coming slide. So you have this diffraction effects of this fine pattern that is going to reduce your resolution to like a couple of micrometer, down to a couple of micrometer. Okay, so this is what generally used in most of the research labs. This is a process that you do in a mask aligner, but of course your resolution is always limited by the diffraction limit. Okay, and the third method is a projection method. It's called projection lithography, where you have mask, then whatever the light beam coming out of the mask has been demagnified and focused down to the sample using a sophisticated optical system. Okay, here you can actually get the resolution to few nanometers, and this is what is used in microfabrication in the industry. And there is no contact with the mask, there is no mechanical align, there is no hard pressing or soft pressing of the mask with the material. So mask is relatively pristine and clean, and you can have very high throughput during using this method, but it's actually extremely expensive, and it's a complicated equipment, and it's not really, used in academic settings. This is mostly up to the industry scale. Okay, and recently there's another method has come up, which is called maskless lighter. There is no mask at all. What you have is you have something called a chip. Okay, this is called DLP chip. It's actually out of micro mirrors, and this micro mirror you can control using a computer. This is what is there in your DLP projector. So whatever pattern you can feed into the computer, this DLP chip can actually, these mirrors can align and project that onto the substrate. So what you have is you have a light source, which is usually UV light source, and all the associated optics with that. Then this has been, guided to the micro mirror. The micro mirror will actually project it onto a sample. Whatever the pattern here, that will get projected down to the sample. And there are of course optical systems which used to demagnify this down to the sample. So this is probably the best method in academic settings because it's relatively inexpensive. You don't require a mask at all, and you can create whatever pattern you can draw onto the computer. You can create that. You can get that down to the substrate, and this whole mask stage is being kind of removed, and this process is also very clean because there is no direct contact with anything. So you can just put the chip under it. You can control the whole machine using computer. You just feed whatever patterns you want, and that will get projected. It's a very fast process and very scalable. And this also involves a lot of mechanical movements because the working stage need to move to get a larger pattern. Okay, but that is not a huge disadvantage because nowadays the systems come with extremely accurate stitching mechanisms down to few fraction of a micrometer to few tens of nanometer using laser interferometer controlled stages. Okay, so these are the summary. This is summary of all the various modes of the photolithography. Okay, process. Now, a few examples. So you have the this is a workflow. You have the plain wafer. Once you coat with the resist, you can get some discoloration is there, some new color, some interference pattern is there. That is the interference from thin film of resist. Okay, and then you can do lithography and define whatever patterns you need. So the blue regions are exposed. Okay, and after that you can do a metallization stage where you deposit metal on top of it and remove the resist from the rest of the places. So you get this pattern, whatever you have drawn on the wafer. Okay. Instead of using this is a conventional mask aligner lithography. Okay. Instead of that, you can use a maskless writer, something like what we just explained, and you can draw this wheel, chariot wheel, using the computer. You can just take a pattern from internet or from whatever the CAD file you have, and you can project that onto the substrate, and you can get that developed. This is like 400 micrometer is the size here. So the whole, that is the center of the chariot wheel is like 200 micrometer. Okay. Now, what you have here is after you develop, you deposit metal on top of it. That deposition process also we will outline in towards the end of this lecture. And of course, then you strip the resist on the rest of the places. Then you got this wheel transferred onto the wafer. Similarly, this is example where the emblem of the IISER Thiruvananthapuram has been drawn using this projection lithography system. So now we have gone through the basic lithography process for creating patterns down to few micrometer. For example, here, these thin lines like a couple of micrometers in width, and here the center of the chariot wheel is like 200 micrometer, and these arms are like a few micrometer wide in length. Okay, and this photolithography involves a light, and when you use light, you are bound to have diffraction effects. So there are two kinds of diffraction effects that affects the resolution of lithography, especially photolithography. One is the near field diffraction, which affects the hard contact mode or soft contact mode lithography. And then you have the far field diffraction that affects the projection lithography, okay, the resolution of the projection lithography. So when the pattern or the mask is in contact with the substrate, you're expecting that the whole pattern will completely get projected onto the or exposed onto the substrate accurately. For example, if you have a pattern which is like a rectangular region, okay, and ideally when the distance between the mask and substrate is 0, you are expecting that the light will fall uniformly in this region, okay, on the substrate. But what we have is something called near field diffraction pattern on the substrate. Even though this is the width what we have on the mask, but the near field diffraction, because inevitably you'll have some really small gap, okay, between the mask and the substrate in the soft contact mode, even though you are pressing it against it, but you still have like a very small gap, which actually can come from the non-uniformity of the thickness of the photoresist or some small angle, whatever is the reason, and you're also not in the hard contact mode anyway, okay, so you're going to have this small gap, okay. So what you will get on the substrate is a pattern which looks like this, okay, and that will get deformed as you increase the distance. So this is for 2 micrometer, and when you go to 4 micrometer you will get this, 6 micrometer you will get this. So you can see that the pattern is going to spread, okay, further and further, and now you're getting much further, the intensity is spreading much further into the region where you don't want the light, at the expense of intensity reduced where you want it uniformly, okay. So close to like 14-15 micrometer, this is what you are going to get, where this is what you wanted, okay. So the resolution is severely limited by this near field diffraction, okay, and the minimum resolution is given by this formula, where K is a parameter depending upon the photoresist and other details, which you can take as 1, it is close to 1. Lambda is the wavelength and G is the gap. So when the gap is 0.6 micrometer, when the gap is 1 micrometer, your resolution is something like 0.6, and as you increase the gap, the resolution is also going to reduce, and eventually it hits like a couple of micrometer or more when you have like a 20 micrometer gap between the mask and the substrate. So in the soft contact mode or proximity mode, your resolution is severely affected by the near field diffraction, and the best you can get, as I discussed in the previous slide, is like a couple of micrometer. It is not limited by the completely by the wavelength. It is actually limited by the near field diffraction effects. Okay. Now let's look at what happened in the far field case. In the far field case, what we have is the abyss limit, which is basically the Raleigh's criteria, and the effect of refracting index also built into it. Okay, that is abyss limit. Okay, so here the magnitude or the resolution is of the same order as the wavelength. You can do slightly better than your near field one. Okay, but it's decided by the diffraction effect, far field diffraction effect, and the minimum dimension is given by this formula, where K1 is like a less than 1, usually 0.5 to 0.75. Lambda is the wavelength, N is numerical aperture. So you can basically engineer or play with the numerical aperture by using mediums with a higher refracting index to reduce the limit. Okay, reduce the or make the pattern finer. So what you wanted is something like this, but what you are going to get is something like this. Okay, because of the diffraction. And it is not only that it's going to spread the pattern, it also will have non-uniform intensity, and how the pattern is developed also going to depend on the region. Okay, for example, the center part will get more dose, whereas the edges will get less dose. Okay, so the dose itself is non-uniform around in all these diffraction. Because of all these diffraction effects, dose itself, the amount of light which is falling on is going to be completely non-uniform, and that also will affect the quality of the pattern, not only the resolution. Okay, so this is the effect of far field diffraction. Okay, in neither case, your resolution is compromised severely by the diffraction effects. And there is another limitation that comes from the depth of focus. Okay, especially for the projection lithography. If you have like regions on the sample with various heights, okay, for example, you have some edge profile on the sample and you want to draw some patterns onto it. So you have regions with different heights on the sample. Okay, so depth of focus is given by this formula, where it is completely focused in here. Okay, this is over focused here and under focused here. Okay, so this depth of focus sigma is also depending upon the wavelength and also numerical aperture. Now here, depth of focus is more when you have larger wavelength. Okay, so you assume that you can play with a slightly larger wavelength and get a larger depth of focus. But now that will be under the expense of this resolution here. Okay, because this criteria says the resolution is also limited by the wavelength. So if you try to increase the depth of focus, make the depth of focus better by increasing the wavelength, that will be under the expense of this resolution here. Okay, so you can actually increase the depth of focus and also the resolution by playing with the numerical aperture by using medium which has a higher index of refraction. Okay, just to reduce the numerical aperture. That is what generally is done. Okay, so wavelength you cannot touch very much because the wavelength is mostly fixed by the characteristic of the resistive, because the certain resistors are basically sensitive to certain wavelength region. Okay, so the wavelength is kind of fixed mostly into the UV regime. Okay, now what you have is the numerical aperture of the optical system. That is what you are going to adjust or engineer to get a better resolution in both the vertical and also the lateral direction. Okay.